Welcome everyone to my channel Skyline. In this video series I will discuss about special theory of relativity, a few topics of STR. Now let's start. From my childhood, the equation that attracts me the most in physics is one of the most famous of physics, and it is E equals to mc square. And also nowadays the equation, a question that attracts me is what is time? I ask my juniors first what is the time now, and then the second question, what is time? The second question is a tricky one, and the answer is also tricky. No one had answered it yet truly and completely. Even Albert Einstein said that if he lives for another 30 years, he could live with this question, thinking about it, thinking about the answer of it. Now, why I am saying these about the equation, about the question? Just because it belongs to the branch of physics, special theory of relativity, which I am going to discuss. Okay, let's carry on. And before going towards special theory of relativity, we first need to understand the basic need of STR, why it was formulated, what was the need to formulate a theory like special theory of relativity. So, I mean, what are the drawbacks of classical physics? Why Einstein had to formulate a new theory? So, let's carry on. Now, before going to the drawbacks of classical physics, I will try to describe some of the terms that will be required to describe anything in STR or classical physics. The first term is event, and the second one is frame of reference. Now, an event is something that occurs independent of the frame of reference or the coordinate system that is required to describe it. An event can be the collision of two balls, the collision of two particles, the lightning of a small bulb, the sound of a mic, anything. And a coordinate system which I will use to describe an event, that is the frame of reference. So whenever we talk about frame of reference, we divide it in two categories. The first one is the inertial frame of reference, and the second one is a non-inertial frame of reference. And here, while talking about STR, the special theory of relativity, we will talk completely about the inertial frame of reference. So let's go and visit inertial frame of reference. What is it and what are the applications of it? So let's see. An inertial frame of reference is a frame where Newton's laws are valid. Now, whenever we pronounce inertial frame, we pronounce one thing, inertia. And we get the concept of inertia from the first law of motion of Newton. And that law states something like that: when no external force is applied on some body, the body will try to keep its motion on. That is, if it was stationary, then it will keep on stationary state, and if it were in a motion, it will move in a constant velocity. And obviously velocity is a vector, it will move in a constant velocity in magnitude and also in direction. So from that concept we can define the inertial frame of reference. If some body, obviously an isolated body, is not in action of any force, then it will continue in its motion, it will continue its velocity. If it were stationary, then it will continue to be stationary, and if it was in motion, then it will continue in a constant velocity. It gives us intuition about one thing, that more than the stationary state, the constant velocity is a greater useful concept, because we can use the stationary state to be a zero velocity concept. Now we can prove that if the laws of motion or the laws of Newton is valid in one inertial frame, then it is also valid in another frame that is moving with a constant velocity. So that has some significances. So let's prove first that thing, that the velocity does not show any impact on the inertiality. Here I have taken one frame of reference, and I have assumed that this frame of reference is in stationary state. But this stationary state is not the absolute rest. Something like we are living on this earth, and to me the earth is in a stationary state, but obviously the earth is rotating about the sun, so earth is not completely in a stationary state. But to me, if I put a coordinate system or a reference frame on this earth, that will be in a stationary state, and another frame of reference that I can put on a train that is moving, so to me that frame of reference will be moving. So let's take another frame of reference that is moving. So we can take in any arbitrary direction, but by orientation of the first frame of reference, I can take it in my comfortable direction. How? So if I take a coordinate frame like this, in this direction, so this is not along any axis, not along x, y, z. This is along an arbitrary direction. But I have the choice that I can use a frame like this. So here I can take x, here I can take y, and here I can take z. So there is no problem choosing the primary orientation of the frame I am using to be in a stationary state. So I am erasing it, and I will consider only the simplest case. So I have two frames. The first frame is stationary, and the second is moving with a constant velocity v along the x-axis. I am calling it x prime, this is y prime, and this is z prime. So I can get the transformation equations something like x prime equal to x minus vt. How? Suppose there is an event happening here, okay, or along the x coordinate, but as the frame is moving along the x-axis, so the event's x coordinate will be this is x, and this is obviously vt, because this frame has a velocity v, and with velocity v it has traveled for a time t, and this is x prime. Okay, so x prime equal to x minus vt, from this we can get, and the y prime and the z prime coordinates are same as I assumed, and as Newtonian concepts are built, we assume that t prime equal to t. That means an observer on this frame will have the same clock as an observer who is on this frame. So the clocks are synchronous, they are running at the constant speed, and they will show the same time at any instant. So these are the equations, and these equations are known as the Galilean transformation equations. From this we can take the derivative with respect to time, because derivative with respect to t prime and t are same, so we can just take the operator d by dt prime the same as d by dt. There is no problem going through that. So I'm erasing the picture. Here I can take the derivatives, that is dx prime by dt prime equal to dx prime by dt, just because t prime and t are same. So this will give the derivative of this quantity. So this is dx by dt minus v. V is a constant. The second equation is dy prime by dt prime is equal to dy by dt, and dz prime equal to dz by dt. So here we get the velocity is not constant in both the frames. So velocity is a frame dependent variable. Now if we take another derivative with respect to time, what will we get? Let's take it. So d square x prime by dt prime square is equal to, so this is same as taking another derivative with respect to t. So this will give d square x by dt square, and here we will get d square y by dt square, dt prime square is equal to d square y by dt square, and the third one d square z prime by dt prime square is equal to d square z by dt square. Now another thing of the classical physics, there it was assumed that mass cannot be changed. Mass is a constant. So even someone is running with some velocity, the mass will be constant. That is the assumption of classical physics. So we can multiply m in both the sides. Here also we can multiply m on both the sides, here also. Now if we sum up these three equations, what will we get? We will get something like m d square r prime by dt prime square equal to m d square r by dt square. Here r prime is the position of that location where the event is happening in the second coordinate system, that is moving with a velocity v, and here r is the coordinate of the position where the event is happening with respect to the stationary frame. So what does this mean? This is simply ma prime is equal to ma. We can take the vector notation also. So this is f prime is equal to f. So if f is constant in both the frames, that states that Newton's law is valid in both the frames. This states the concept of the classical relativity. Now one thing to notice, if you are on a train and you are not looking out of the window, then you can never tell anyone that whether you are moving or not. And this is the classical relativity, and you can tell only when you look outside the window that the earth is stationary and you are moving with respect to the earth. So again we can understand that we can have infinite number of inertial frames, just because we can take any arbitrary velocity, 1 meter per second, 2 meter per second, 3 meter per second, and all will be inertial. Thus we can define the inertial frame of reference, and there are some consequences. We will discuss it next. The consequence of the concept of inertial frames, we can conclude that the frame we took to be stationary can also be moving, and we cannot understand whether it is moving or not. So all what we can understand the relative motion, but not the absolute motion. So that is the relativity of the classical physics, or the Newtonian relativity, that states that we can measure only the relative velocities, not the absolute position, absolute motion, or absolute state. Newton's laws, the Newtonian or Galilean relativity, is well applicable in our daily life, and till then, till the discovery of the STR and some experiments, it were highly used, and even today it is used in our daily life. There is no exchange, but there were some drawbacks that forced us to think about developing something new, something better. So what are the drawbacks? So first I will discuss about some theoretical drawbacks. The first one is I should talk about the Lorentz force. So what is it? We know the equation F equal to QV plus QV cross V. That is the force on a charged particle when the particle is moving with a velocity v in presence of an electric field and a magnetic field. Now, the Newtonian concept on inertial frame states that the force will be same on the particle if it moves in a constant velocity. But here we see that the term v is here, and if frame is moving with a constant velocity with respect to another, then v will not be the same, so force will be changed. And again, if I ask anyone what is the origin of this B vector, this is the magnetic field vector, and anyone who has the knowledge of class 12 magnetism, he will answer that magnetism arises when a charged particle moves. And what do I mean by moves? It has some velocity. So a charged particle that is stationary in an inertial frame can be moving in another. So the V field is not same from the classical concept in one frame and in another. So F is not constant in one frame and another. So it is a drawback of classical physics. And the second drawback is from the Maxwell equations. He deduced the speed of electromagnetic radiation, and also it is the speed of the light, and it was c is equal to 1 by root under mu naught epsilon naught, where mu naught and epsilon naught both are constant, so c is a constant. But as we learned from the Galilean transformations, if an observer moves in any arbitrary direction, so he will not see the light moving with a constant speed. How? Suppose an observer is moving with a velocity v and light is coming from here with a velocity c. So what will be the relative velocity of light with respect to that observer? Obviously that will be c plus v, that is greater than c. And the other can also happen if the observer moves in this direction with a velocity v and light comes from this direction with a speed c. To him the speed of light will be c minus v, but how can it happen? But here we don't get anything like that. Both are constants. So if it were true, then mu naught and epsilon naught must change when we change the inertial frame. That is, when we change our frame to an inertial frame that is moving. But if mu naught and epsilon naught change, force on the charged particles or whatever that will change. From the Coulomb's law, we know Fe is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, so there is a term epsilon naught. Obviously I am taking the magnitude. Okay, so when we change the frame, Fe will change because epsilon naught is changing from this concept to follow the continuity of this concept, and also the magnetic force that will also change because there is a term 1 by mu naught. Here we see that the Galilean transformation equations or the classical physics which were followed by each and everyone in physics, in mechanics and engineering, mechanical engineering throughout more than 200 years could not satisfy the Maxwell equations and Lorentz equations. So it was against electromagnetism. And now there are some more examples, there are some experimental examples. So let's take an example. Suppose we have a charged particle, let's take an electron, and the electron is forced to move in some potential. If the potential is 10 mega electron volt, then from the equation EV is equal to half m v square, we can get the velocity acquired by the electron, and we will get the velocity to be 0.9988 multiplied by the velocity of light or the speed of light. Now as the v varies as v square, so if we multiply v 4 times, that is, now if we apply the voltage to be 40 mega electron volt, then as the classical equation predicts, the velocity had to be the twice of 0.9988 c, and it is much more than 1, that is much more than the speed of light, 1.997 c. But in reality this does not happen. When the voltage applied is 40 mega electron volt, the velocity acquired by the electron is just 0.9999 c. So there is an increment by 0.11%, not by 200% as predicted by the classical physics or the Newtonian concepts. So the classical concepts fell experimentally and also theoretically. That's where we needed something extra, something more which is better than the Newtonian concepts. Okay, Newtonian concepts are okay at low speeds, but at high speeds it fails dramatically. That's why Einstein's STR is more appreciated than Newtonian concepts. Okay, thank you. This is all for this video. In the next video I will start with the concepts of developing ether, and then how it was discarded, and then I will go to the bottom lines of STR and the concepts of STR. Okay, thank you.